now, I think. Now? No. No. So this is the Yeti default mic. Now. Now is the microphone, exactly. I don't know why I've set up the speaker to be... This should be just the computer speaker. There you go. I think that's fine now. We're basically... what I've been working on these past days, these past weeks is sort of here and there. A bit more about the I'm kind of like a bit, just walking around the position space, momentum space concepts, and trying to make up sort of a better and more solid understanding of these things, right? Because to me it's like you mostly always work in position space. That's the feeling that I have, right? So you have wave functions that depend on position and time, but then there's also momentum space. What I assume is momentum space is what you then you would have a wave function that is a function of p, right? That's fine. And one of the things that I wanted to understand is why there is this Fourier transform relationship, and how do you get there. I've also was refreshing the concept of operators. I mean, if you go to the Wikipedia, you kind of have this thing here where they position momentum spaces. And so the momentum operator is given by this. That's what the Wikipedia page says. By Fourier transform. The road to reality, Penrose. These are the eigenfunctions. And then so the wave function of position is, and now basically this is what's confusing. So these are the eigenfunctions of the momentum operator. This is what's confusing me. What does the operator have to do with these, with all these? Here they say the reason is the wave function is very closely related to the Fourier transform in the constant frequency domain is because the quantum mechanical particle has a frequency. The frequency is proportional to the momentum. Describing the particle as the sum of its momentum components is equivalent to describing it as the sum of the frequency components. Okay, so that's why they... Okay, this is... I had never paid attention to that sentence more in detail, but it's actually fairly simple. That's why. It's because the momentum is related to is proportional to the frequency. That is kind of... That is interesting, right? Why is... If the wavelength of a photon is known, the momentum can be calculated. What is the sense of that, though? So that will take me to a video? No. The blank, the way. Quality of relationship between the wavelength and the frequency of a photon and its momentum. We don't know this. That doesn't tell me. The Bragg hypothesis suggests a particle can be associated with a wave of momentum. How does one arrive at this concept of the momentum of a wave? That's a good question, exactly. I understand the classical definition of momentum, however, I do not see an obvious extension to an object such as a vibrating guitar string. The Broglie, I can't, how do you pronounce that? Is saying that if I have a vibrating guitar string and the wavelength of vibration decreases, then the momentum of the guitar string I guess this is just from a physical standpoint, thinking about like from a physical standpoint, it's like momentum is proportional to velocity in a way, right? So I mean, if you think about momentum of something that's vibrating, it's something that's then proportionally related to how close it is to stop vibrating, right? So this means the higher the frequency, the more momentum it has, because it's vibrating a lot. The lower the frequency, it's almost like the wave is almost not there anymore, right? So I think that kind of makes that makes more sense. Okay, that is yeah, that's fine. So the quantum mechanical particle has a frequency proportional to the momentum. Is it really just this? That's why the Broglie equation given above something known to arbitrary position. So this becomes clear when we ask ourselves how we can transform from one representation to another. And this is where here I feel like they're missing stuff. Suppose we have a three-dimensional wave function in position space, then we can write this function as a weighted sum of orthogonal basis functions. So far so good. It is clear that if we specify the set of functions psi kr, say as the set of eigenfunctions of the momentum operator, the function the set of functions, say as the set of eigenfunctions of the momentum operator. Why would you do that though? Holds all the functions and this is for an alternate description of the state psi. This is the momentum operator, and these are all the eigenfunctions. but we're integrating over K space. So it's very much not, this is very much not clear. So if I had like a more like a so you have a wave function, you can specify, you can basically represent this wave function as basically a weighted sum of the orthogonal basis functions. And what we're saying is that if we are using if these are eigenfunctions, we say they are the eigenfunctions of the momentum operator. Why would you do that? Why would they be why would that make sense? Why would that make sense at all? Why would you do that? Why the momentum operator? Because the momentum operator, operators in quantum mechanics, so they correspond to making a measurement, right? Operator. So essentially, in physics, an operator is a function over a function over a space of physical states into another space of physical states. The simplest example of the utility of operators is a study of symmetry, which is a group, blah, 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 yeah. Operators in quantum mechanics. So, physical pure states in quantum mechanics are represented by unit norm vectors. In special time evolution, so the time evolution in this vector space is given by the application of the evolution operator. Okay. Time evolution operators. Any observable, any quantity which can be measured in a physical experiment should be associated with a self-adjoint linear operator. The operators must yield real eigenvalues, since they are values which may come up as the result of the experiment. Mathematically, this means the operators must be Hermitian. The probability of each eigenvalue is related to the projection of the physical state into the subspace related to that eigenvalue. See below for mathematical details about them in the wave mechanics formulation. And differential operators. Differential operators. So in mathematics, the differential operator is an operator defined as a function of the differentiation operator. It is helpful as a matter of notation first to consider differentiation as an abstract operation that accepts a function and returns another function. With mechanics, commutators, yeah, essentially. So essentially, what an observer, what this is doing is the the operator must yield a value. So you have, so essentially what it's saying is, you have the position operator, you have this position operator, which is what you would which is essentially what you would so when you apply the momentum operator, kind of when you apply the momentum operator, what you're trying to do is you're trying to get you're trying to get an eigenstate as a result. So these kind of make sense. It's defined as in there's a derivative of the position in a way. And so and these are basically the eigenfunctions with eigenvalues. Okay. I guess this is just telling us is that you can express that the wave function in position space is the same as taking a wave function, taking this psi wave function, basically. Okay, so taking that. Yeah, this thing, but this is not known, right? So, and then it's just basically saying, well, whatever it is, right? Like, but you have these coefficients that are multiplied by the eigenfunctions of the momentum operator, and integrated, right? Just as a sum, and that. And the other way around, conversely, a three-dimensional wave function in momentum space can be expressed as a weighted sum of orthogonal basis functions. Well, actually, in here, like these things. Okay. So in here, this is what you know. So essentially, imagine you know it. So what you're doing is you're expressing it as a, and then as a the coefficients, you're expressing it as as the multiplication of the eigenfunctions, and you're integrating and so because you're integrating, you end up just you basically end up just with R's, with space. So all you're saying is the way you're constructing it seems obvious. I sometimes just think about I'm thinking about this from the wrong perspective, I think, but it's really this. So what you're saying is, well, I can see that. I'm just trying to establish a relationship. If you express it as if you express a wave function in position space, together with a set of functions, say as a set of functions, momentum operator, the function holds all the information necessary to reconstruct three-dimensional wave function in momentum space. Conversely, a three-dimensional wave function in momentum space can be expressed as a sum of orthogonal bases or as an integral. With eigenfunctions and eigenvalues are. So similar decomposition. So these are the eigenfunctions. It just keeps bothering me because I'm not so sure I understand this step. So three-dimensional wave function in position space. So this is the wave function in position space. We can write this function as a weighted sum of orthogonal basis functions. Exactly. Or in a continuous case as an integral. It is clear that if we specify the set of functions psi k r, say as a set of eigenfunctions of the momentum operator, I think let's focus on that step. If we specify the set of functions of orthogonal basis functions, if we specify this set of functions as the set of eigenfunctions of the momentum operator, okay. So so what we're saying is eigenfunctions. Because the thing is here is these are eigenfunctions of the position basis, right? Because you have a wave function in position space. But now they're saying, what if we set them to be the eigenfunctions of the momentum operator? That's what's confusing me. Then psi k holds all the information necessary to reconstruct psi r, and is therefore an alternative description of the state. In this case, what you know is the phi. This is the known thing, right? What you're looking for in this case is psi and position space. You know, it's just this is what's confusing me. So you have this one, and you say, well, if I express that, if I basically have, if I just have my function in position in momentum space, but why should I hold all the necessary information to reconstruct psi of r? It's this is it just keeps confusing me. Transform momentum space. As far as I confront the case, where eigenvalues are continuous rather than discrete. Specifically, it's time to generalize the all-important formula of the superposition of eigenfunctions. Yeah, so that's what. Okay, so that makes sense, right? So this we understand, where psi n can be any complete but discrete basis set. Typically, psi n have been energy eigenfunctions. That rises to infinity on both sides, trapping the particle and quantized in all. Realistic potential functions are never infinite, so they're but there's an even more important example of a complete basis set that's continuous. The momentum eigenfunctions. I have the momentum eigenfunctions. Complete basis set that's continuous. The momentum eigenfunction. I'm still not sure I grasp the concept of a continuous basis, but okay, let's just ignore that for a second. So. Where p can be any real number, these functions are also energy eigenfunctions of a free particle. If this collection of basis functions were discrete, we could express any other function. Okay, so that is again, this is where I get the same. I kind of get lost there, right? So wrong. Yeah, wrong because if this collection of basis functions were discrete, we could express any other function psi x in terms of them. Why though? The momentum eigenfunctions. Why can you do that? Why can you just the collection of basis functions were discrete, we could express any other function psi x in terms of them by using a sum. But because p is continuous, we need to replace a sum by an integral. In this formula, I've also switched from the letter c to the standard symbol phi and factored out a constant from phi for a reason that I'll explain in a moment. Okay. The important thing to notice is that instead of a discrete set of coefficients, we now have a continuous function that encodes how much of each basis function is incorporated to the wave function. This function phi p has a name, the momentum space wave function. So that is the momentum space wave function. What I don't get is why can you do that at all? Like why can you say this collection of is discrete? Well, I have momentum eigenfunctions are the momentum operator. The momentum operator is an operator. Okay, but the momentum operator is, so my assumption is in here. The momentum operator is an operator that is defined in position space. Is it momentum? Maybe that's why you can do that. Yeah, the momentum operator is the operator associated with the linear momentum. The momentum operator is in the position representation, an example of a differential operator. Yeah, so this is the momentum operator in position space. Essentially, this is the momentum operator that you can apply to a wave function that is expressed in position space to basically obtain the momentum. I don't understand why can you do that at all. functions are if this collection of basis functions were discrete, we could express any other function in terms of them by using a y. Why? Because basically well, it's like saying, you know, there are multiple ways you can express. You have a set of eigenfunctions. You have a set of eigenfunctions, so that's kind of like your basis, right? So you have a set of bases, and then it's just your choice, right? That's kind of your reference. It's like your reference frame in a way, right? So if you have these eigenfunctions, and then you can come up. Basically, you need to find the coefficients, and then yeah, exactly. And so you can specify the wave function of position. It's just a given basis, right? So but then wouldn't these be true for any other basis? You know what I mean? Essentially what it's saying is then if so this function is incorporated into the wave function. This function has a name, the momentum space wave function. For every ordinary wave function there must be a corresponding momentum space wave function. And how do we find phi p for a given psi x? Again, think about the discrete case. There, to find a particular c, and you use the Fourier's trick, multiply by integrate over x and exploit the orthonormality of the basis functions to kill off every term in the sum except the one we want. Let's try the same trick here. Okay, that's for another day, I guess. Now, whatever. That's how you reverse that. I know why it's Fourier transform, because of the frequency proportionality. It's fine. You know what bothers me? What bothers me of these all is just the very fundamental basic understanding of the, I guess, the eigenfunctions, right? And the fact that like why can you do that at all? The momentum. Guess it's your choice, right? It's your choice of basis. You have a basis that's the momentum basis in position space. since the position is an zero quantity, the position operator has a complete set of eigenstates. This spans the state space and also consists of orthogonal eigenstates because position operator is Hermitian, which holds the causal relationship there. Random operator. This is what's kind of escaping my it's what's escaping my understanding at the moment. Is basically why can you say oh, I lost that text, whatever. Why can you just say suppose we have a three-dimensional function position space. We can write this function as a weighted sum of orthogonal basis functions, right? So you have a set of orthogonal basis functions, and you can always write down these as a function of those, right? And so you're saying, or in the continuous case, like these. If we specify these functions to be the eigenfunctions of the momentum operator, then the function. I guess I guess okay, that maybe helped. So if you're picking these up as, I guess that's kind of, and that's just the way you define it. You actually define the wave function in momentum space as in like being this guy here, because essentially is what so if you have the set of it's complicated. If you have the eigenfunctions of the momentum operator, these are basically the sort of the orthogonal, like these are all the different momentums, right? Momentas that you could have, right? As an eigenfunction, so to say. The function, then this function phi holds all the information necessary to reconstruct this guy. Just that's the idea. Is this is what you want to find. So what you're saying is you can express a wave function in position space with whatever whatever set of orthogonal basis functions, right? If you just happen to pick the ones that are the momentum operator eigenfunctions, then the coefficients that you'll need to apply, this guy here, the coefficient you need to apply, actually, this is then the wave function of that's what you can call the wave function of momentum. Yeah, I guess that's it. I guess that's and then you do your well, I guess what you would do is the other way around. You would say what probably was said here is like you have these, and so if you just pick these to be the eigenfunctions of the position operator, and I guess the position operator in momentum space. Yeah, that's the position operator in momentum space. Exactly. Now I think I connect it. So yeah, and that's how you would do it here. So you would say, I take the position operator in momentum space and I say I'm going to express my wave function. I have the psi r. I multiplied by I'm curious if that would just work like this. And I understand the construct, right? So the concept of expressing something as a sum of in the structure of like you have eigenfunctions, and then you it is just because it's the geometrical basic case of you have like, you know, it's like your bases, and so you basically say from how much of each component you use to represent what you want to represent. And so in this case is, you know, a level upper from an abstraction perspective, right? Because you're playing here with eigenfunctions. So you have these eigenfunctions, and then you're saying how much of these functions are you really using to represent that function. And if you're, I guess if you're in momentum, if you want to get the momentum space wave function, and you know a given set of you know your, so what this is saying is if you know your wave function in momentum space, we could do an example next time probably, you know, in position space, you know, wave function in position space, then you multiply these by the eigenfunctions, and then you get the stuff in position space, essentially, in momentum space. I think I get it. Well, at least I'm feeling more comfortable about it. R space. You have the eigenfunctions of the position operator, and you would essentially do that. You can do that. You can do that with whatever operator, right? So I guess you can do that with, I don't know, whatever operator. It's just in this case it just happens to be Fourier transformish just by nature, right? Because of the fact that it's proportional to to the frequency of the wave. And you just see this because the wave, you just see this here because you end up with the Fourier transform expressions just because of the nature of the eigenfunctions of these operators, the eigenfunctions of these exactly of these operators. The fishy thing still here is the concept of why is it so that if I use the eigenfunctions of the position operator in momentum space, that the coefficients, okay, yeah, exactly, the coefficients essentially no, the coefficients hold all the information, that's true, but like hold all the information of position, right? I feel I've done a bit of progress, but it's not a bit, but quite some. But I'm still not 100% comfortable with these. See you next time.